Welcome to the deep dive. Today we're really digging into something crucial for anyone looking at data: null and alternative hypotheses.
Absolutely, they're fundamental.
We had a request to unpack this, so we're going to explore why they're so essential and how they, shape our entire analysis. Okay, let's jump in.
Sounds good. So basically, statistical analysis is all about testing ideas, right? Claims. And these hypotheses, the null and the alternative, they give us the structure to do that properly.
And the timing is key, you mentioned.
Yeah.
Defining them before collecting data.
Yes, exactly. That's critical. You absolutely have to define them before you peek at the data.
Why is that so strict?
Well, it's about objectivity. If you see the data first, you might even unconsciously tailor your hypotheses to fit what you've already seen.
Ah, okay. Like drawing the bullseye around the arrow after you shot it.
Precisely. It prevents confirmation bias. Setting them first means you're deciding what constitutes strong evidence beforehand. It keeps the whole process honest.
Right. And you also said these hypotheses dictate the expected distribution of the test statistic.
Yeah.
What did that mean practically?
Okay, so the null hypothesis, that's usually our starting assumption, like no effect or no difference. It gives us a specific scenario.
A baseline.
Exactly, a baseline. And if that baseline were true, we can figure out how our test statistics should behave, what kind of values are likely, what are unlikely.
In the alternative?
The alternative offers, well, the other possibility, or possibilities, what we suspect might actually be true instead. These two opposing ideas frame how we evaluate the data we collect.
Okay, let's talk p-values and alpha, the significance level. What if the p-value lands exactly on alpha, say 0.05 on the dot? Do we reject the null then?
The standard convention, the rule of thumb in most fields, is yes. Reject if p is less than or equal to alpha. So if it equals alpha, that's just meeting the threshold for statistical significance.
So it counts.
It counts. You'd reject the null.
Now, the null isn't always zero effect, is it? Can it be something else?
Oh, definitely. That's a common misconception. Sometimes the baseline you want to test against isn't zero.
Like what? Give us an example.
Sure. Imagine a factory claims its new process reduces defects to below 3%. Your null hypothesis wouldn't be zero defects or even no change. It might be the defect rate is 3% or higher.
And the alternative would be?
The alternative would be the defect rate is less than 3%. You're testing against a specific non-zero benchmark.
That makes sense. What about one-sided alternatives? When we only look in one direction?
Right, a one-sided test is when you're only interested if the effect goes in a specific direction. For example, does a new drug lower blood pressure, not just change it?
So you're focusing your statistical power.
Exactly. You get more power to detect an effect in that one direction you care about. But the trade-off is...
You'd miss an effect in the other direction.
Completely. If the drug unexpectedly raised blood pressure significantly, a one-sided test looking only for a decrease wouldn't flag that. You're making a specific bet.
So choosing that alternative carefully is pretty important then. What happens if it's poorly defined?
Well, a vague alternative can lead you astray. You might reject the null, get a significant result, but it doesn't actually answer your real question. Or it might be too broad, making the finding less informative. Clarity is key.
Let's touch on a few specific tests. Paired samples, like before and after studies. How do hypotheses work there?
Yeah, for paired tests, think measuring the same person twice. The null hypothesis is usually that the average difference between the pairs is zero.
So no change on average within individuals.
Right, and the alternative is that the average difference is not zero. Or you could do a one-sided test, like the average difference is positive.
Okay. And chi-square, goodness of fit. What's the null saying there?
Goodness of fit. The null hypothesis there is basically saying that the proportions you observed in your sample, well, they match some expected set of proportions.
Like, do the observed colors of candies match the company's claimed percentages?
Exactly like that. Does your data fit the expected model? The alternative is simply that it doesn't fit.
And one more, ANOVA, comparing means across multiple groups.
Right, ANOVA. The null hypothesis in ANOVA is quite broad. It states that the means of all the groups are equal.
All of them.
All of them. HA1, MEA1 is equals no, 2 equals 3, and so on. The alternative is just that at least one group mean is different from the others.
So ANOVA tells you if there's a difference somewhere, but not specifically where.
Precisely. If you reject the null in ANOVA, you usually need follow-up tests to find out which specific groups differ.
This is really helpful. One last, maybe philosophical point. Can we ever really accept the null hypothesis?
That's a really important distinction in how we talk about results. Technically, we don't accept the null hypothesis.
We fail to reject it, right?
Exactly. Failing to reject isn't the same as proving the null is true. It just means our study didn't provide enough evidence to convince us it's false.
So maybe the effect was too small for our study size, or maybe there really is no effect.
Right, we just lack sufficient evidence to make a strong claim against that baseline null hypothesis. It's a subtle but crucial point about what statistical tests can and can't tell us.
Okay, that really clarifies things. So wrapping up, this whole process hinges on setting up those null and alternative hypotheses clearly and doing it before you analyze anything. It's the foundation for drawing valid conclusions from data.
Couldn't said it better, it guides everything that follows.
So as you look at information or studies, maybe think about what underlying assumptions are being tested, even if they're not explicitly stated. What's the hidden null hypothesis? Thanks for exploring this with us today.